Okay, so I'm gonna do gen RSA keys. One advantage now that hopefully you'll like is that this is gonna be like OpenSSL. It's gonna generate our files already instead of having the number. Like when we looked at RSA from scratch, you literally had the numbers, right? However, for the practical, make sure that you know how to use both approaches, okay? The RSA from scratch and these, because it may be easier to factorize to calculate the prime numbers on one versus the other. Okay? Break RSA basically. All right, so let's go ahead. Library from crypto should be familiar already. So from crypto dot public key import RSA from crypto import random. Okay, just in case we need it. Let's go ahead and generate the key. This hopefully is easier nowadays with PyCrypto DOM. So we invoke RSA and do something like generate. And then, as you might expect, 2048. Remember, that's an important parameter because it establishes security, right? So we've established that with FactorDB, we cannot factorize ends that were created when we have a seed of 1024, right? We were not able to break it. I don't think we were able to break 512 either, were we? Can't remember. Yeah. But it has been shown in the literature that 124 can be broken. Okay, so let's just go with 2048. We won't be breaking keys today. We're just showing how to use public and private key one more time. Okay, this is the last time. So let's generate private key here. So it's going to be private underscore key, and it's in key. So we can say, I really should call that variable keys, but it's okay. All right, so I'm going to do key dot export key. By default, the implementation of PyCrypto DOM just assumes that this is the private key, okay? So the export key. And then for the public, it would be public key. It would be from key. That's why I was saying maybe calling it keys would make a little bit more sense. But we can say key dot public key, and this is all lowercase. Public key dot export key. Just like that. Okay. And now once we have these, we can just write this out to the files so that we can have our PEM files. So then we're going to say public. Yeah, let's do private first. Private out, right? Open, and just give it a name. So I'm going to call it private.pem. Private.pem, comma, and we have learned that everything is bytes here in cryptography, right? So we do WB. So then we're going to do private out dot write. And what do we write? We write private key. Private So we write this out to the file, then we can just close it. File out. Oh, sorry, not private out. Dot close. Make sense? Then we repeat the same process for the public key, pretty much the exact same thing. They call it public out. Out. This is going to be open public.pem. Public.pem. WB. Public out dot write public key. And then we do public out dot close. That's it. All right. So hopefully this by now, all of this should make sense, right? If anything, Python was way harder in the beginning of the semester to the point that now it's like so easy, right? I hope. All right. So let's go ahead and do this. So let's see if we can generate the files. Okay. Okay. No errors. Good. And we have our PEM files. We can look at them. From your knowledge of private and public keys, this is right on track. It's larger, right? The private over the public. So you should be familiar with that. And now let's do cat of private. Looks like a big file, which makes sense because our seed was really big. Yeah. And then we're going to do, oh yeah, cat public. Public. Oops, sorry. Public.pem. It's much smaller. The nice thing about this code, PyCrypto Dome, is if you think carefully, you now have Python and a powerful cryptography library. So what can you build? Lots of things. Okay. Because you have all the power of Python, all the libraries of Python, and a solid cryptography module or library. Okay. So you can try to prototype different applications. All right. So that's the keys. So what's the next thing that we probably want to have? We want to have RSA encrypt and decrypt, and we would be using this to exchange the symmetric key, right? That's exclusively why we're using it. So that makes sense. That's the next step. I may tell you to exchange the key, right? So I'm going to say, Ben, generate your keys, share your public with Nathan, right? And then now achieve confidentiality of this message, right? Your name on it. And then what? You need to encrypt the symmetric key, right? And send it to him. And then you open it with the proper key, right? This is how the demo is going to work, okay? No mystery there. Any questions about that? Okay. So let's look at how do we do the encrypt first. Yeah, so all right, let's take this approach. Right. So nano RSA encrypt. P1. Okay. So from crypto dot public key import RSA. Okay. Now let's just say data. Remember the byte, the B. And then here, what would this be? This would be the symmetric key. Okay, I'll even write it here. In general, symmetric key. Okay, and then you would get this from, we had it already, I think. Right, so in theory, we have it in, where did we have it? AES key, right? Cat AES key, remember? But it's a byte array. But actually in the code, we also need to give it a byte array, B. So actually it works, right? So you can either hard code this, or you can just read it from that file and load it here. Do you see what I'm saying? Make sense? Okay, so I will just hard code it, but it's perfectly easy just to read it from the file, and that way everything is in files. Okay, so just some value here. Okay, some value. Keep in mind the I think it was 16 bytes, right? So actually, let's be consistent with that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right. So just do that. So now, what do we want to do? We want to read in the file, the key. We're going to encrypt. So F. You can even say something like, if I'm encrypting, then what type of a key do I need? Someone's public key. If you're working with someone, keep picking on you guys. So Tim, right, and Mark, let's say, right? So Tim is sending a message to Mark and wants to send that key encrypted. What does he need?
His private key, and then the other person's public key.
The other person's public key, right? So for this example, the other person, so you can say Bob, right? And that way you know whose key you need. Got it? Because this message can only be decrypted with their private key, right? So something like this. I'll just do generic like this, but putting the name is not a bad idea. All right, and so we're gonna do open. Open, and then I think it was called public.pem. Public.pem. All right. So then we can say public. Public. I usually say something like string or byte array just to indicate that this is not the final object. And so we're gonna take F encode read, or F encode pub, sorry, dot read. see that? So we're reading in the key, and we're just going to load it into PyCrypto DOM. So it's coming from a file. We need to load it. So we would do there. Let's close F encode pub. So dot close. And then we're going to do public key underscore key. And it's going to be what? RSA dot import key. Public key string. And what's happening here is we're going from the file to a variable to loading this in the RSA object. Okay, so now it's part of the RSA object, and we can, there's a data structure basically. Does that make sense, guys? So now we can try. I'm going to try this implementation, but I do have another one. Now that I have the key, I want to just perform the encryption, right? So it would be, so I'm going to use here, although we're still using RSA, right? We're still using RSA. We're going to use an implementation of RSA called the PKCS #1 OAEP. Okay, so that's think of it as that you take the RSA map and then somebody implemented specification so and so. So basically the PKCS #1 OAEP is an asymmetric cipher based on RSA. And it has a type of padding based on something called OAEP. So it's still RSA, it's just, an implementation. Very much like PyCrypto DOM is an implementation of all the algorithms, okay? Some of you want to do like Blowfish, I think you said in your project. That's just an implementation of a symmetric algorithm, right? So they're still all coming from these same ideas. They just, in the actual implementation, they have efficiencies of the code, etc. Okay. So basically, this can only, it is described in reference RFC 8017. Okay, so you can read up on it if you can Google that. It can only encrypt messages slightly shorter than the RSA modulus, which is only a few hundred bytes. Does that sound contradictory to what you would understand for RSA? That it can only encrypt messages slightly shorter than the RSA modulus? Or do you think that's correct? Okay. Sounds right. Exactly. Why? We've said RSA is not for encrypting movies, right? We've said it many times. It is only really for encrypting the keys, the symmetric key. Remember, it's not designed for movies or things like that. For those kinds of things, it's better to use XOR and AES. Okay, hopefully that makes sense. All right, so anyway, yeah, that's the approach. So I'm going to use that version. You're going to see me reference it, and it's just like a very solid one that people are using or recommending that you use when you're using PyCrypto DOM. Obviously, you're not going to use PyCrypto DOM in something that you implemented, because although RSA is solid, you never know if there's a bug in PyCrypto DOM, intentionally or unintentionally. And so you want to watch out for that. OpenSSL is probably the only thing that you should kind of trust. And even there, you got to be careful. Okay. So anyway, especially if you're sending very sensitive information. All right. So now we're going to bring in this library. And this is how we're going to try to implement RSA for both encryption and decryption. So we can go still, it's still part of PyCrypto DOM. So we can just say from crypto dot cipher, sorry, dot cipher, import PK CS1 OAEP. Okay. So now we're going to initialize our cipher RSA. So here we already have the key. Now we can just say cipher underscore RSA. And we're going to invoke PKCS1 OAEP. Okay. We're going to say new, it's an object, so it's got the same format that we've seen before, new. And we're going to initialize this object with the public. Make sense? All right. Now that we have that part, let's proceed to try to encrypt our message. So it would be the data, right? That data. So we're going to go ahead and do cipher RSA dot encrypt and we are going to encrypt data. Okay, got it? So we encrypt data here. And this is going to give us the encoded data. But remember, you're going to be working with a partner. You need to send them all these files correctly. So we want all of our code here to read and write from files as much as possible. So we're going to write this to a file. And this will be the cipher. Okay, so we need to create file out here. File cipher out. So that's going to be equal to open encrypted data dot bin, and we can conveniently write bytes, right? That B becomes very helpful, right? And so we can do WB. And now, just like we've done before, we're just going to write to our file. So we can just say file cipher out dot write. We are going to write encoded data. Encoded data. Oops. Data. And then close the file. We're almost done, right? What do we have left? RSA decrypt and then the digital signature. That's all we have left. And we've covered pretty much everything. And as you can see, the scripts are short. So let's do file cipher out dot close. Got it? Any questions? All right, so Control X, Y. Now we're going to run it. Huh. Okay. Change this K to an uppercase, maybe. Try it again. All right, so now if we do ls space -l, we should have a bin file, this one, right? No, that's a encrypted data bin. Okay, that should be the file. If we do cat encrypted data bin, you can see it is encrypted. All right, what's the next one? Decrypt. Okay. So RSA decrypt should be similar. Shouldn't take that many lines of code. All right, so let's go ahead and do nano. I'm actually gonna do CP RSA crypt RSA decrypt .py. So I'm just going to modify the code. So now I should have an RSA decrypt. So we can do nano RSA decrypt, right? All right. So we need crypto public import RSA. We got that. We need crypto cipher import PK CS1 OAP. So we use that to encrypt. We're going to have to use that implementation to decrypt. What are we going to read? We're going to read in the encrypted data. All right, so let's go over here. Do I need this one for this? No, of course not. I wouldn't even know it. So you can get rid of that. Instead, the input needs to be the cipher. So I'm going to do file in open. I think it was called encrypted data. Encrypted data .bin, correct? And then we should do, because it's bytes, we should do RB for read bytes. Okay. Then we do encoded data file in dot read. So this allows us to load the cipher into our memory. Now, what do we need? We need a key, right? Which key do we need?
Private.
Private. Very good. So you're going to decrypt. So we're going to say F encoded private. No, that's just to help you out. Open private.pem. Okay, private.pem. We're going to read it. So F encoded private would go into what I'm calling private key string. Right, just like that. And then we do F encoded private dot close, right? And then we're going to invoke RSA import key. So RSA import key, and we're going to give it private key string. And let's change this name to private key so it's more obvious. Okay, so now that we have that, what would be the next logical step? We invoke PK CS1 OAP, which, as we have stated, is just an implementation of RSA. And we're going to do new, and here we provide private key. Okay, so then that creates cipher RSA, and then cipher RSA now, instead of encrypting, we are going to decrypt. Okay. And at this point, we don't really need to save a file. You can, this is just the key that you would enter, although you could save it in plain text and read it into the next step. It's up to you how we do it. But really, we're just going to cipher RSA decrypt. what do we decrypt? Encoded data. Right? Okay. And that gives us actually plain data. And the last part of this might be to print plain data. Does that make sense, guys? Is this clear enough? All right, so let's go ahead and try this one. Control X, Y. Python. Does that look right? It does, right? Yep. Questions? That's it. So that's PyCrypto Dome. The last script, the only one we haven't done, if you notice, I've done gen RSA, encrypt, decrypt RSA. I've done AES, and I leave it to you guys to try other modes of operation and other DES, for instance. Instead, you know how to do integrity. The only thing, there's one thing I haven't done. What is it that you guys would need?
Digital signature.
Digital signature, right? So that was the last concept. Well, let me see that one. Yeah, signature. It's not that long, so I know we end at 40, but if you stay a few minutes, we can just do it, and then you can go practice, and then we can do the demos on Thursday. How about that? Make sense?
Mhm.
All right, so this one also, I think we can do this with PKCS, I believe. So we're going to assign something. Okay, so let's go ahead and try it out. All right, let's call this one signature PKCS. Again, PKCS is an RSA implementation that's more robust. So let's do nano signature PKCS. And by the way, this is already on the GitHub. All right, so start. We are going to do from crypto dot signature import PKCS 1 underscore 15. Okay, that's again just another version, if you want to think of it that way, implementation of the ideas of digital signature. And then you're going to do from crypto.hash import SHA-256. Okay. Oh, and that should be uppercase. SHA-256. And we can do from crypto dot public key import RSA. You know that you need hashing functions, and you know that you need RSA for digital signatures. Okay. So we're going to read in a key first. So we're going to do F equal open, and oops. I'll just write here your key dot M. Okay. So what key do you need? Comma RB, right? And then we do my key F dot read. Okay, then we can do F dot close. And then we already know how to load this into key. So it's going to be RSA dot import key. my key. Okay. Then what is a digital signature? We talked about it. We would sign what? A contract or something like that. We could do it with confidentiality or without, right? So let's think, I'm just going to hard code the message here, but you could also read it from a file, just in the interest of finishing. So I'm going to do message, again, the B for byte array, single quote, and then message to be signed. You guys see that? So that's what we're going to sign. Remember, plain text, okay? And that's okay. Then I'm going to calculate a hash, as you can see. So I do SHA-256 dot new and then message, right? Remember, if you look at the diagrams in the slides, we would calculate a hash first. All right. And then what do we do with the so-called hash? We create the signature. And the signature would be RSA, right? But in this case, we're using PK CS1_15 dot new, and it takes key, right? And then we do dot sign. What do we sign? Not the message, not the key, the hash. All right, so we sign the hash. You see that? That's the idea. I like this example because other examples like abstract a lot of this, but this one lets you do this. All right, so that's it. That signature is it. What would you do with this signature? Send it to your friend, correct? How can you do that? Pickle dump. Okay? Or write bytes. Either one should work. But you guys already know how to do that. Now to wrap up, on the receiver end, right? What do we need? So Bob sends it to Alice. Now we have Alice. So we're going to do F equal open. It's going to say another key dot pem, right? Dash RB, right? And we're almost done. So then we read it. I'm going to do another key here equal RSA dot import key. And then I'm just going to do F dot read. Okay. I'm reusing F, but I closed it in the previous one, so that should be okay. And then I can just close F again. Okay, guys? So I loaded the key into another key. And now I can, what do I need to do with the message? I'm going to hash it. Right? So, wait, not hash it. I'm going to verify it, sorry. So I'm going to do PK, so I can do result, maybe res, PKCS1_15 dot new. What does it take here? It takes another key dot verify. Okay. It takes in the signature. We've got the key. And what else did we? It's one thing that we've done this before, right? When we did the digital signature, we had the signature. We have the key, the appropriate key. There was one more item that we needed to have. The message, right? The unencrypted message. Do you guys remember? And what do we do to that encrypted message here? We need to hash it. So I'm gonna do H equal SHA 256 dot new message, right? We would have the message, right? And then now we just plug this one in here. H. And basically, we would want to know if it checks out or not. Got it? So one quick way of doing this is do a try catch. So you can do try. This will work. So do 1, 2, 3, 4. And then if it checks out, basically, you can print true, else, or except. 1, 2, 3, 4, print false. It doesn't actually provide the true or false itself, but this will work. So you'll be able to corroborate your digital signature. So if it checks out, it'll print true. If it does not check out, it'll print false. Does this make sense, guys? As far as the digital signature, I kind of left it a little vague with the key and another key in the hopes that you guys have fun with this and play with it. All right, but you know how digital signatures work. So I've given you all the PyCrypto Dome problems. Basically, then the homework is assigned. Do this, and then we'll next Thursday you can do the demos. So I need to sit with someone, with a group, with partners, and I'll ask you questions, and you will do the demo on your computers. And it'll be a first come, first serve basis, right? And hopefully we'll get everyone on that Thursday. Otherwise, it'll continue the following Thursday. But everyone needs to do everything, okay? Does that make sense? All right, so that's it for today. I've given you PyCrypto Dome. Look at the GitHub. There may be other examples in there with slight variations. Get a feel for it. And yeah. Don't forget the exam on Tuesday and then these demos on Thursday, please. Okay, that's kind of the plan. If we make progress there, we'll be able to move. Well, do you have a question? Yeah.
So for the demo, is it possible for us to use